Since we've been talking about high energy radiation, this is a good time to take a bit of a detour and talk about a field of meteorology that deals with how the Earth's atmosphere interacts with the sun, and that is the field of space weather. Now, the sun is continually releasing highly energetic and charged particles away from the sun, and these moving particles are known as the solar wind. Now, let me explain a little bit more of where these come from. Perhaps you've heard of sunspots on the sun. If you look at a picture of the sun, you have some darker regions on the surface of the sun. These darker regions are actually storms on the surface of the sun. Not quite the type of storm we deal with. They're not big clouds and rain and lightning. That's not what we're talking about. They are disturbances in the sun's magnetic fields. These magnetic fields are arranged around the sun that keeps most of the sun together, but every once in a while there's a little disturbance and creates these. My laser pointer. If there's a disturbance in the magnetic field, then occasionally large masses of the sun can actually come off in a small amount of time, called a prominence, or if it actually leaves the sun's surface, it's called a flare. Now, what's going on here, like I said, these are these disturbances on the surface of the sun. As a result of these disturbances, the temperature is actually a little bit cooler. And remember from earlier in chapter 2, we saw that the amount of energy that's released depends on the temperature. Since the temperature in these regions here are a little bit cooler, then they don't emit as much energy, so they are not as bright. Now, because the sun is just so bright, our eyes take these little spots, these regions, these storms, and say, even though they are still emitting light, it's not as much, so it looks darker because it's just not as intense as the rest of the sun. And since it's darker, it just looks like there's a spot on the sun. That's what a sunspot is. And like I said, there are disturbances in the magnetic field, and if the disturbance is large enough, then you can get a large, intense bursts of charged particles coming off of the sun. Now, the solar wind generally just goes off into space and doesn't really do anything. Doesn't affect anyone. But occasionally, they're sent off in a direction that's just right, that it will intersect with the Earth. And if it does, it has the potential to cause a lot of problems. If it were just these particles straight towards the Earth, these particles are so energetic, they could be completely devastating to all life on Earth. Life wouldn't be able to continue very long at all, depending on how frequently these storms hit the Earth. As it is, they do affect our geomagnetic activity, the Earth's magnetic field. They do affect communications, and they do affect weather. We've had many military operations that have been hindered, we'll say, because a solar flare hit the Earth, caused geomagnetic activity, which made it so that you couldn't use radio. And as such, you couldn't talk back and forth. So it happens. It has happened many, many times and still happens today. So what protects us from these? On minor storms, we'd have all these problems with communications, weather, so on. Major events, life would be devastated. So why aren't we? Why isn't the Earth completely lifeless because of these storms? Well, we have a shield, a magnetic field. Now, the way that this works is if you have highly charged particles that hit a magnetic field, then these charged particles start to spiral around the magnetic field lines and move toward the pole. Okay, that's what would happen with a normal magnet. But it turns out that the molten core of the Earth actually generates a magnetic field around the Earth. So the Earth is just a great big huge magnet. So when charged particles come around the Earth, these charged particles hit the magnetic field lines and start spiraling around, and they start collecting near the poles. And the Earth itself is safe, no problems. But what about these regions up near the poles, where near the magnetic poles? The charged particles are all going there. Doesn't it just make it worse? Well, it just turns out that when all those charged particles start collecting there, they don't really have anywhere to go. They have to release that energy, and so they do in the form of light. This is where we get the aurora. An aurora is where these highly charged particles hit the magnetic field, are diverted, go to the poles, and they release their energy, and you get these waves of dancing lights. So here's the whole picture. You have the sun with the sunspots, these magnetic storms on the surface of the sun. They create flares, and so you have solar wind that pushes a whole lot of highly energetic particles towards the Earth, but before they actually reach the Earth, they hit the magnetic field, are diverted towards the poles, where they then lose all that energy in the form of light, and everyone is just fine. And we get a cool show out of it as well. Hope you've all been able to have a chance to see an aurora. They're really quite spectacular to see. Occasionally, we do get events strong enough to see auroras here in Ephraim, in central Utah. It's not very common, but it does happen. It's happened a few times just in the last couple of years. Here is another interesting thing to look at. This is the number of sunspots identified in a given year. Notice it goes through a cyclical pattern. You have high numbers of sunspots, and then low numbers of sunspots, high sunspots, low sunspots, so on. Basically, this is corresponding with high amounts of solar activity, where you get a lot of solar wind, can cause disruptions in communications and weather and so on. And then you have minimal solar activity. The solar wind is actually quite calm. And then it goes up again, goes down. Every 11 years, we cycle from high activity to low activity back to high activity. About every 11 years. There have been very few exceptions to that. It's pretty regular. I'm recording this video in 2025. We are just coming out of a maximum period. These last couple of years have been really exciting. We've been able to see auroras here in Ephraim because of that. But yeah, if you're watching this video after 2025, then you're going to be seeing the solar activity decreasing. We'll have fewer sunspots and fewer aurora events in general. And that completes chapter 2. We are all done with that. And so we've talked a lot this chapter about how the Earth is heated, how the atmosphere helps to retain that heat using the greenhouse effect. We've talked about the energy budget. We've talked about conduction, convection, radiation. There's a lot there. Again, I have to emphasize, this is probably the most important chapter of the entire course, because this chapter is the basis for everything else weather. You want to talk about thunderstorms? Well, what makes a thunderstorm? It is convection cycles and balances in energy. So make sure you take the time, study carefully everything in chapter 2, and good luck with everything here, and we'll see you in chapter 3.